is also to show you some patterns. So when you see these libraries, hopefully you will see some similarities in how they behave, how you use them. And yeah, we will do a summary in the end. What does it all have to do with functional programming? So yeah, I have just 2 slides, just an introduction so that you know who I am. Yeah, I'm a software engineer writing Scala. For a long time before that, I was doing Java. I work at Software Mill, which is a consulting company based in Poland. We all work remotely for various industries, various clients, using fancy technologies such as Scala, Kafka, Cassandra, doing blockchain, machine learning, and CRUD applications, of course, as well. Yeah, and I'm doing some open source projects, so check them out. And we have a blog with a whole Scala section if you'd like to read more about what we are doing with Scala. Okay, so that's about for the introduction. The application that we are going to write is going to be a very simple application which will write to the database and expose an API endpoint. We are going to store the likes for programming languages. So the schema that we are going to work with is one table which will contain the languages, and one table which contains the likes and has a foreign key for the language, right? So here, username, an entry in that table will say that the given user likes the given language and that the like was created at the given time. Okay, so the goal is to store data in a database and to expose an API endpoint which will allow us to write that data. So, going to code. So we are going to, as I said, we are going to use 2 libraries. That's not that interesting about Scala FMT. We are going to use doobie for accessing the database. We are going to use tapir to describe the endpoint. We are going to use Zio to work with side effects, and we are going to use HTTP4S to expose the HTTP server. So let's start by actually describing how we are going to store the data. So let's start with doobie. So the first thing that we need to do is we need a way to actually insert a language into our database. So we write a method upset language with a given name, and a result will be a data structure of type connection.io, and we return the ID of the language that we have just inserted. So what is a connection.io? A connection.io, as I said, is a data structure. It's an immutable data structure which describes operations that need to be done on a database in order to perform some changes. So in our case, this will be a description of what should we do on the database in order to insert a language. Right? You might be familiar with an I/O wrapper in Scala, or sometimes it's a task or something like that. So an I/O wrapper usually represents some side effects which are lazily evaluated. So here we also have side effects, right? But they are not arbitrary side effects. These side effects need a database connection in order to be run, right? So these are side effects which need to be run in the context of a SQL connection. Okay, so in order to upset a language, what we will do is we will run a SQL. So we will write some SQL by hand. So what we need to do is we need to insert into languages in the ID and name columns, and the values that we insert are, we are going to generate a random UUID, and we are going to insert the name. Now, because we don't really want to write a simple insert, we want to write an upsert so that we don't have to check every time if the language is there. So what we will do is we will also say that if there's a conflict on constrained languages name key, then we say do update set name. So we are doing a dirty trick here, just to touch the row so that we can return the ID of the modified row. And now we have to say doobie if what kind of data to expect from that query. So we are actually going to expect a single value, and that's the ID of the returned of the returned of the inserted language. So that's an update which returns with generated keys UID in the ID. So that ID over here corresponds to that ID over here, right? Okay, and that's all. Why do we get a compilation error here? Values, yes, thank you, IntelliJ. Cool. Languages. See, it's nice to have this built in. Okay. Why is it still red? It shouldn't be red with unique generated keys, because there's only one value. Okay. So the combination of type-safe programming and IntelliJ helped us to write this piece of code. Okay, so what you might have noticed here is that we are writing SQL by hand. This might seem backwards, because, you know, it's 2020 and now we are doing SQL by hand, but it allows us to write any SQL we want, right? Imagine trying to express this kind of SQL using, I don't know, some higher level DSL, right? That would be quite scary. Probably we would have to verify that the SQL generated by that code generator actually works. So here we have the freedom to write any SQL we want. SQL is a very nice programming language, and we should use its power when possible. And that's one of the options with doobie. We can also get SQLs generated, but that's another topic. Okay, and the second query that we need to write is inserting a like, and who likes what. So we will want to insert that a given person likes a given language. It's also a description of side effects on a database, so it returns a connection IO of unit. So what we are doing here is we are first upserting the language that we are liking, and now we need to sequence two operations on the database. The first operation is inserting the language. The second is actually inserting the like. So we always express sequencing using flat maps, and here is no different. So we flat map the connection IO value. That's the ID of the inserted language, which we can use in our query. So now we insert into likes. What were the column names? ID, language ID, username created, the 4 columns. And we insert values, again a random ID. Okay. Who, no, the ID of the who and instant.now. Okay. Yeah, I guess that's it. Now we have to say that again it's an update and that we don't care about the return value, which by default will be the number of modified rows. And it compiles. Nice. Okay, so we have our descriptions of our SQL queries. So what is important is that the result of running this method, if we run that method now, what would happen is only some memory would be allocated. So nothing in the database would change. Invocation of that method creates a data structure which describes what should be done on the database, right? We haven't specified here how to actually connect to the database. We haven't specified how to get the connection and so on. These two concerns are separate. Okay, so now that we have the query, let's describe the endpoint which we'll use to actually save our data. So we will do that using tapir. That's another library which we've been working on at our company, and that's why I'm using it. Also because it's really good. Okay, so yeah, let's create our endpoint. So our like endpoint, and the description of an endpoint is again a data structure which describes the structure of the endpoint. So it's built incrementally. How it works is that we start with an empty endpoint which doesn't map any values from the request and doesn't map to any values into the response, and then we refine it to capture the necessary information. So our endpoint, that will be a post endpoint, and we will secure it with a bearer token. So on the input, what we want to extract from the request is the bearer token header, and we want to get that value. The second input, we are specifying that our endpoint should be exposed on the API/like path, and we want to extract a JSON body which maps to like data, and like data will be a case class saying that a username likes a given language, right? And as the output, we say that if there's an error, like an invalid authorization token, and on the output we want to use a string body, and yeah, that's it. So what we can do is now we can ask IntelliJ to infer the type, and we'll see what the type is here. So the type has 4 type parameters, and what the type says is the first type parameter are the values that we extract, that we map to from the request, right? So from the request we extract the bearer token and the body, right? That's a tuple of 2. In case of an error, we return a string. So that's the value that maps to the response, right? So that string corresponds to the string body over here. In case of success, we don't return anything. So in case of success, you would just get a 200 OK, and that's it. Nothing, no special headers or bodies and so on. And we are not doing any streaming, so that's not important. OK, so now we have described our endpoint. And again, it's a data structure which just contains the metadata of the endpoint and doesn't contain any logic, right? So the next step to do is actually supply our endpoint with some business logic. Okay, and that's where the third library comes into play. So we would like to expose our endpoints using the HTTP4S server. So the HTTP4S server basically takes a bunch of functions which take an HTTP request and convert them to a response, right? So these HTTP4S functions contain both the mapping between, so they contain the information of what we want to extract from the request, but they also contain the business logic, what to do with that data, right? So in order to convert our endpoint into such an HTTP4S function, we need to provide the logic which converts the inputs to the outputs. Okay, so what we'll do is we will define our route, which will be an HTTP routes. So this HTTP routes value is that's the HTTP4S type. To constrain side effects, we will use the ZIO task. The ZIO task is a description of an arbitrary side effect which might throw arbitrary errors. So what we are going to do is we are going to take the like endpoint, and we are going to use the to ZIO route extension method. So the to_ZIO route knows how to interpret. It's like an interpreter which takes the data structure describing the endpoint and converts it into an HTTP4S endpoint. To_ZIO routes. Sorry. We can ask IntelliJ for tips on what's the type of the function that we need to provide, and the type is as expected. So we need to provide a function which takes a single parameter, which is a tuple of string and like data, also of our bearer token and of our body, and we need to provide an IO value, a ZIO IO value, which produces either an error in the form of a string or a unit which is success, right? So we can now deconstruct our input into token and like data. Okay, so if token is equal to 1, 2, 3, 4, that's very basic security. Then we will do something. We will actually store it in the database. The easy case, if it's not 1, 2, 3, 4, then we fail, and we say invalid token. Now, if it is 1, 2, 3, 4, then we actually want to insert the data, right? So what we do, we call insert like data username, like data language, right? Correct order. Who and what? Yes. Okay. But so we have created a description of what to do on the database. We still need to do it, right? That's here we have just created a data structure describing the operation on the database. Now we need to convert it into a side effect, which actually, takes a connection, starts a transaction, does the changes, commits, and so on. So what we need to do is we need to run the transaction. So that's done with the transact method, and it takes a transactor. We will create a transactor in a second. Actually, let's create it now because IntelliJ won't allow us to do anything interesting. So a transactor of type transactor of task. We can create one given some configuration parameters. So here we need to specify the driver, PostgreSQL.driver. We need to specify the connection string, the FP database. We need to specify the username and the password. As you can see, I'm the fan of basic passwords and basic security. Okay. So now we have our transactor. So the transactor is the structure which contains the details on how to connect to the database. It contains the connection pool, right? And what the transact does, again, it's an interpreter. It takes the data structure over here, and it interprets it so that it turns it into a side effect, which describes taking a connection from the pool, starting a transaction, executing what's described by the inserting the like. So there are two operations over there, if you can remember, that are sequenced, right? The insert like, where's my cursor? The insert like is a sequence of upsert and the insert over here, right? So these are going to be run in a single transaction, right? Whatever the whole description, which is a composite description, will be run in a single transaction because we run the transact on the composite thing. Right, so now we have an arbitrary side effect which can throw an arbitrary error in a form of throwable, and we have promised a string error, so we have to convert these. So we call map error using so the T here will be the throwable. If there's an error, we log it. Error exception when talking to the database, and we log the error, and we just return for the user internal server error. So we don't want to expose the details of our errors to the users, so we will log them, and the user will just see this nice error message. Okay, again it compiled. There's some red code here. Why is there some red code here? Brace again. Cool. Thanks IntelliJ, and thank you. Okay. So what we have done, we have our database operations, we have the description of the endpoint, we have interpreted the endpoint as an HTTPS route. The last thing that we need to do is we need to actually we need to start the server. So that will be now a main function. So what we need to do is we need to, HDFS works with any kind of effects which integrate with CATS effect. And Zio has a compatibility layer between Zio itself and CATS effect. So what HDFS needs is, for one of the components is a thread pool on which to handle the connections and so on. So we need to take the Zio's thread pool and provide it to HDFS, and that is done by extracting the Zio runtime, Zio.runtime .flatmap. So we extract the runtime, and it's an implicit value. Runtime any. Okay, and thanks to this implicit value, it will be converted to a context shift from CATS effect, and that will be provided to HDFS, and that will be used by HDFS to actually serve the request on these threads. So now we create a new HDFS server. So we need to provide some boring details like the port on which we want to connect, 8080 of course, and localhost. And then we need to provide the actual routes, router, so /maps to our route over here, like route. Okay, otherwise not found. And now serve.compile.drain. Okay, still not happy? I forgot about, yeah. So because we are in Zio, we have to handle errors. So the signature of our main method says that we need to return a description of an effect where all errors are handled, right? So this type parameter specifies the type of errors that our side effects might throw. So creating a server might throw an arbitrary error, and here we have promised no errors, so we have to somehow recover from that. So, and we have to return an int, which is the exit code, right? So if this ever ends successfully, it will never end successfully because it's a bind. But if it does, we return a 0. And if there's an error, we catch the error, and we again log it, logger.error exception when starting server t, and we map it. I've lost the sorry, dot map, and we map it to 1. That's our exit code. Okay. Happy now, I guess. Let's try compiling it. That's always like 90% of success in Scala is getting your code to compile, and then just like 1 unit test and you're done. Okay. Yeah, unused. Swagger, yeah, that's what we are going to use now. So we could run it and we could test it manually, but we will do something else. We will actually create a very quick UI for our application. So the UI we are going to use is we are going to expose Swagger documentation. So what we can do is we can take the description of our endpoint here, which is just a plain data structure. So far we have interpreted it as a route, right? So we have coupled this with some business logic, and this was converted to an HDFS route. Another thing that we can do with the endpoint is convert it to documentation, right? So we can take this description here, this data structure, and actually convert it to docs, to a YAML file. So what we will do over here is we will create a YAML which contains the open API, the Swagger specification of our endpoint. So to do that, we need to import the interpreter, which is like a separate thing. So this time I will just write the imports. All the other imports have been there from the beginning because there's a couple of them. Source YAML. So we need 2 imports. That's the imports to actually bring in the interpreter for converting the endpoint into an open API data structure. And the open API data structure is like a reification of the whole open API specification as Scala case classes. And that's the serializer of the data structure into YAML. So what we will do now is we take a list like endpoint to open API, best languages of 2020, version 1.0. And yeah, that's it, to YAML. To YAML. No? Minor detail. Okay, cool, thank you. So we have created our YAML. We still have to expose it, right? So we still need to expose some kind of endpoints, which will... Why is that red now? Whatever. We need to still expose an endpoint which will expose the Swagger UI. So we combine this with a Swagger route, which we'll define here. The Swagger route, again, it's an HTTP routes of task, and we created by using the new Swagger T4S. And what we need to provide here is the YAML to HTTP. Nope. Routes, simply, okay. Routes of task, okay. And yeah, compiled, okay. So that's the Swagger route. So that route exposes all of the assets, the CSS files, the images, the HTML of the Swagger documentation. So here we expose, so now we expose 2 routes, right? We exposed our like route, which was interpreted from our endpoint, and all the Swagger things. Okay, compiling. And suspense. Finished. Okay. It's red, but we don't care. It shouldn't be red. Like, did IntelliJ broke suddenly? What? Whatever. Okay, let's run it, and we'll see if it works. Okay. Okay, I guess we have it open. Let's open it up. Not found, yes, because we need to open the docs. So that's the default context path under which Swagger is exposed. So here we have our API, the best languages of 2020, right? API-like, we can try it out. First we have to authorize using, let's say, 4567. We are a poor hacker. So I'm saying that Adam likes Scala. Execute. What did we get in response? Bad request. Okay, invalid token. That's good. Security works. So now we log out and 1, 2, 3, 4. And now the best kind of testing. So testing on production. Let's see. 200, I guess. Yes, 200. Okay. Wait. Let's go to the database. Not so fast. We still need to see if there's anything here. Yes. Okay. Now we can clap. Okay, and we can see if our abstract works. So let's say that Tom likes JavaScript. Well, yeah, whatever. But Mary likes, I don't know, F#, let's say. But she also likes Scala. Right? So now we should have a couple of entries over here. 5 minutes, okay. Yeah, so we have a couple of entries here, and our languages still, there's no duplicates. So this works fine. Okay, cool. So this worked. So how can we summarize this? So what we've seen is these libraries have a couple of things in common, right? So at the basis, we have worked with immutable values, right? So in case of doobie, this was the description of the database operations. That's an immutable data structure. This is like a tree of case classes, right? Inside this tree, you can find the queries that need to be executed, or a specification that it's a sequence of 2 queries that should be run in a single transaction, and so on. We've seen task, which is a description of IO, which is a description of arbitrary side effects. So that's task IO. So task is an alias for IO, which throws arbitrary errors. Again, it's an immutable data structure which describes arbitrary side effects. Endpoint, again, an immutable data structure which describes the structure of our HTTP endpoint, right? These are all immutable values. And then we had some functions. So some very basic ones like map of let map, available both on connection IO and tasks, with which we can sequence 2 effects together, right? We had transact, which interpreted, which is an interpreter. It interpreted our connection IO description of database operations into an arbitrary side effect, right? We had to routes, again an interpreter, which interpreted our endpoint data structure into a function which was the HTTP4S routes, and to OpenAPI. Again, which interpreted one data structure into another data structure this time, which was the OpenAPI documentation, right? And in a way, that's the essence of functional programming, right? In functional programming, the main construct is the function, as the name suggests. Usually the functions operate on values, and usually these values are immutable, so that we can call these functions multiple times safely. And that's the case here, right? So if you want to do functional programming, just use functions and immutable values, and you are done. It's that easy. So yeah, and I had one more slide. The basic technique that we have used here is that we have separate, like typically when you use Spring, for example, right? When you execute a query, you do it in one go, right? You have the connection pool available, and you just issue a query to the connection to the connection. Here we have split it in 2, so we have separated the description of the problem, be it describing the SQL queries, or be it describing the endpoint, or be it describing the side effects, and we have separated it from its interpretation, right? So we interpret it as either as arbitrary side effects, as routes, as documentation, and so on. And this separation gives us an additional degree of freedom, because once we have this problem described as a value, we can do whatever we want with it, right? We have various options in interpreting it. And one other important thing, if you look at this code over here, is not what's in this code, but what is not in this code, right? We only have used libraries, and there's no like framework which tells us what to do, right? We are quite free to use any kind of library that we want. We can quite freely combine them, and if we choose one library, that doesn't necessarily constrain us in our other choices. And that's because we always work with immutable values, with functions, which just transform these values, right? So, we don't do anything fancy here, right? We just create some data structures, then we call some over here, like we call some functions. But this can happen anywhere, right? We can do it on a different thread. We can pass these values around, and so on and so on. So we retain a lot of freedom using this approach. Okay, so that's all I had. The whole presentations that you have seen is available on GitHub, the code. If you would like to see a more complete example of like an application where you can log in users, change their passwords, and so on, there's like an application template with a web UI as well called Budzuka. And we run a weekly Scala newsletter if you'd like to stay up to date with Scala news. Yeah, and that's all. Thank you.